can.
I think we should have to turn it off.
Same. No, I don't think so. Yeah, I think now it's. You can hear the speakers. Right, good. Okay, good. Shall we start?
Yes.
Yeah, so the next speaker is Maryam, and she's going to talk about hypothesis selection with computational constraints.
My talk is about density estimation. This is a joint work with Mark Bunn and Adam Smith. There is this fundamental question in a statistic called density estimation. We have a data set that are samples from some unknown distribution, and we want to figure out the density of this underlying distribution that is unknown. Hypothesis selection is a special case of this problem. We are given a set of PDFs or like density functions, or like also known as hypotheses. We want to pick a hypothesis that describes the underlying distribution of the data well. There are a lot of applications for this problem. The important one from a theoretical perspective is cover method. So when you want to learn a structured distribution, you might select a bunch of representatives from that class such that every distribution in the class is close to one of these representatives. And then when you pick those representatives, you can run the hypothesis selection and pick the closest one to learn that distribution. Other practical application for this problem, for example, you have a bunch of density functions that are interpretable, or you can actually have a actionable strategy if your data is coming from those distributions, or these are sort of the true clean distributions, and you want to figure out what is the underlying, like what would be the closest thing to the underlying data distribution. So you could denoise, or you can interpret the underlying distribution. So let me give you the formal definition. We have a set of finite distribution, h1 through hn, so it's finite. And these distributions are known to us. So let's say we know the PDF. You can actually relax this assumption, and even samples from these distributions would be enough. And then you have an unknown distribution P that you only have sample access to. So the goal is to select a distribution inside this class that is close to h hat. So obviously the best that we can do is to select the closest distribution that has distance, I'm going to call it opt to the unknown distribution. But what we actually can hope to get is something comparable to opt and not opt exactly. In fact, we can hope to get sort of a semi-agnostic guarantee for this problem, like alpha times opt plus some epsilon. So what is the difference between hypothesis selection and the standard distribution learning, if you're familiar with this problem? So in this problem, the guarantees of this form, in the standard distribution testing, we just output a distribution, and we are hoping that the distance to be at most epsilon with high probability. In hypothesis selection, we are sort of in this proper case. We want to output something that is within the class. Generally, this is not true for standard distribution testing. The main biggest drawback of the standard distribution learning is that the number of samples you need to solve this problem is proportionate to the domain size of the distribution. So if, for example, you can't really learn distributions in epsilon total variation distance, within epsilon total variation distance, if you have a very large domain or infinite domain. Here, the hypothesis selection problem, somewhat surprisingly, has a sample complexity that is independent of the domain size, and it only depends on the logarithmically in the size of the hypothesis class. And this is a result that is known for many years ago. So what is our result? So in stats, like what people really care about in most settings is understanding the relationship between sample complexity, the number of data points that you have, and the accuracy of the problem. As computer scientists, and especially theoretical computer scientists, we really care about the computational aspects of this problem, like what is the memory complexity and what is the time complexity of this problem. So for the purpose of this talk, I mainly focus on time-efficient algorithm for this problem while achieving the optimal accuracy and optimal sample complexity. So basically, our result is the first algorithm that runs in almost linear time in n, and it achieves this guarantee for the learner. It is known that this factor of 3 cannot be improved unless you have a sample complexity that depends on the domain size, like polynomially to the domain size, and when you are proper. Like when you're improper, you can get a factor of 2, but for the proper algorithms, this is sort of essential. From the very early work of De Vroij and Lugosi, so this is a table that I copied from our paper. From the early work, De Vroij and Lugosi proposed 2 algorithms. One of them achieves a better alpha, but it has sort of higher time complexity. So S here is the number of samples. So the time complexity is roughly O of n cubed. Let's ignore S. And then they argue that, okay, this is a seemingly worse algorithm in terms of accuracy, but it has a better time complexity. And sort of since then, there are several progress on this problem. In particular, there is this algorithm that they have. It is improved. The sample complexity from n cubed is improved to n squared. And then there are many algorithms that a long line of research that they achieve a factor of alpha equal to 9. And they run almost in linear time. This is another work of mine. If you were here last month and I talked about memory efficient algorithm for this problem, this is that algorithm. But today we're not going to talk about that anymore. And also this is like a very good algorithm that has the right accuracy parameter and also sample time complexity, but it requires exponential pre-processing time. There are other algorithms that they use some knowledge of the underlying problem, such as knowing opt. But in this work, we particularly gave 2 algorithms. One of them runs in time and like n over epsilon, if you ignore S, and then the other one has the right time complexity. The first one has the optimal factor, and the second one has a slightly worse factor, but both of them are sort of new in terms of the accuracy parameter that they achieve. For this talk, I'm going to focus on this first algorithm. So let me start with the background. I am going to talk about 2 concepts, Schaffe sets, which you might have already know about, and then the first algorithm that I mentioned, the Lugosi-De Vroij algorithm for minimum distance estimate. So any questions so far? Okay, let's move on. So let's define the Schaffe set of 2 distribution. For 2 distribution, H1 and H2, we define a Schaffe set to be the set of domain elements that one distribution is higher than the other one. Also, the complement set has similar properties, so the order doesn't really matter as long as you're consistent. So here in this plot, these are the set of points that the red distribution has a higher PDF, higher probability. So this would be the Schaffe set of these 2 distributions. So what is nice about this Schaffe set is this is the set that achieve the total variation distance. So the discrepancy, like let's say we look at the probability that these 2 distributions assigns to this set, the discrepancy between those 2 probabilities is exactly equal to the maximum possible discrepancy, and this is exactly the TV distance of 2 distributions. Think of this set as the set that the behavior of H1 and H2 are different, like very different, and it cannot be even more different than this. So that's why it's sort of a nice thing. For those of you who are familiar with the L1 distance between 2 distributions, this is exactly half of the L1 distance. So let's move on to the first algorithm. For that, I need to define a notion called semi-distances. So it's just that semi-distance is just a name that I give it, but think of it as a proxy for the distance between one of the hypotheses and the unknown distribution. So when I talk about Schaffe-set, we can determine the Schaffe-set between the known distribution. The problem is that we don't really know the Schaffe-set between the hypothesis and the unknown distribution. So what I really want is to estimate the total variation distance between Hj, one of the hypotheses, and P. And by definition, this is the definition. And I don't really know like which subset to look for. What I'm going to do is that to use another hypothesis in my set, HIs, as an auxiliary, sort of as auxiliary information to help me to estimate this distance. What does it mean to use it? Like I'm going to look at the Schaffe set between these two distributions, but the discrepancy that I'm looking for is actually the discrepancy between Hj and P. So this is one subset, one particular subset of the domain, and I'm looking how Hj is different from P. So this is the distance of Hj and P from the perspective of Hi. Okay? And because I take up this time in the graph session, I feel like I owe it to you to kind of bring up some graph theory here. So you can think of it as like you define this as edges between the hypothesis and the like a directed edges between hypothesis, and the weight of this edge is essentially this quantity. So generally, this semi-distance is actually just a lower bound for the quantity that I want. It could be underestimating by a lot, but there is one particular edge that Hj has, and that's essentially determining the quality of this hypothesis. And this is the edge that comes from the best hypothesis. So if this is the closest hypothesis to P, the weight of this edge is essentially the best, the quality of this hypothesis. It's very easy to show. It's like you can do it as an exercise, that the total variation distance of Hj and P is bounded by 2 opt plus the weight of this edge. So if the weight of this edge is bounded by opt, I get what I wanted. I get the 3 opt that I promised that I was looking for. So there is this one particular edge that is very important for me. That's what we want to find. So from this slide, I want you to remember 2 things. That the semi-distances are always a lower bound for the total variation distance. And the second thing is that there is one edge that if it is smaller than opt, then I'm done. Like, this is not quite helpful as is, because I don't know I star and I also don't know opt. Like, this is just a theoretic bound that we have. It's not quite, algorithmically, it doesn't really help. Question?
Sure. WIHJ is not something that's easy to compute.
It is easy to compute because the Schaffe sets between the hypotheses we can figure out, and we have sample access to this. We technically can estimate them, but with a small error. For the purpose of the talk, I assume that we have access to them with full accuracy, but you can estimate them up to small perturbations.
So maybe I missed it. What's the access to P that I have? Like, I have conditional samples?
No, you have you have a subset of the domain. You receive samples from P, and you just count the fraction of the samples that end up being in the set, and that gives you an estimate of P of S. Yeah, so this is something that you can estimate. So semi-distances, you can always estimate them very easily with high accuracy. But for the purpose of this talk, I assume that you have them perfectly. Okay. So the minimum, this is the de Broglie algorithm, the minimum distance estimate. What we do, so we are looking for a 3-opt hypothesis. What we do is that we compute the maximum weight that we have among all the incoming edges of Hj, and we're going to call this the score of Hj. And among all the hypotheses, we pick the hypothesis with minimum score. And the proof from here is essentially two-line based on the observation that I told you before. We just we need to show that this particular special edge that I talk about is bounded by opt. Now it's kind of clear. It's always always upper bounded by the score, and the score of hj, I promise it should be minimum. So it's obviously smaller than the score of any other hypothesis, including the best hypothesis, hi star, and the score of hi star is always, as we mentioned, it's always a lower bound for TV, so it's smaller than opt, and so I showed that the special edge of this hj that I output is bounded by opt, so it's a 3-opt things that I want. The sample complexity is log n over epsilon squared. You can see it easily because the semi-distances that I need to compute only require 1 over epsilon squared samples, and to make sure that they are true for all the n choose two pairs that we have, log n over epsilon squared is enough. So this is highly sample efficient. The time complexity of this algorithm as it's written is like n squared, because n squared times the number of samples, because I need to know for every vertex, I need to compute all the semi-distances that are adjacent to it. So now let's talk about our algorithm. So obviously, if I want to compute all the scores, I would run out of time. So I have to sort of settle by picking not the maximum over all possible edges, but a subset of the edges. So we define this sort of current score, which is not looking at all the edges, but just a subset of the edges, and we take the maximum over those edges. And just to be clear, if you just sample randomly your neighbors and then took the maximum, that doesn't really work, because I told you there's one special edge that has all the information. If you sample, it's very likely that you're going to miss that edge. So it has to be sort of a very well-structured subset, but this is what we are going to do. Initially, in our algorithm, all these scores, we start with 0, and then updates happen. What does it mean? It's like we add one edge to this set and just take the maximum of this edge and whatever we know from before, and just increase the current score, which we denoted by W tilde. And it's like you can see that W tilde is always increasing throughout the algorithm. We're always adding. And then at the end, we kind of mimic the behavior of the minimum distance estimate by outputting something that its current score is sort of minimal. It's not exactly minimum, but small. So the main backbone of our algorithm is a bucketing scheme. So we all the scores are always between 0 and 1, and we partition the interval of 0, 1 into intervals of length roughly epsilon. And depending on where the current score of a hypothesis is, it essentially goes to the corresponding bucket. So here, if the W tilde is between epsilon and epsilon 2, then HJ belongs to this second bucket of the buckets that we have. We have theta of 1 over epsilon buckets here. What happens when we select hypothesis HI and try to update this HJ via this HI is that obviously the score could go up and potentially move this hypothesis to another bucket. So the updates come, you sort of shift your hypothesis to higher bucket. And instead of, so the main this is pretty much the first algorithm that, and instead of focusing on a single hypothesis and try to estimate its distance and try to make sure that the distance is good, we are actually trying to focus on the updating hypothesis. So I'm looking for the updating hypotheses that are good. Which hypothesis is a good updater? The one that makes substantial updates, by both qualitatively and quantitatively. So if I have a bucket, I want this updating hypothesis to to essentially update as many hypotheses as possible within that bucket. And I also want those updates to be substantial, meaning that they update by at least additive epsilon, so I can kick out the hypothesis out of the bucket. So long update in a way, like I want the jump to be long, and also many of them. So finally, this is the algorithm. So we go iterate over all buckets, and then iterate over all hypotheses. So when I'm saying iterating over all hypotheses, these are the updating hypotheses. And then I check if the HI is going to substantially update. A substantial fraction, let's say constant fraction. And if I just check by constant many sample, I can check if it's like a substantially good updater, if by just in O of 1 basically. And if it is a good one, I'm going to perform all the updates that this hypothesis can do. And the hope is that by doing this set of updates, at some point my buckets is emptied out. And if it is emptied out, I'm good, and I move forward to another bucket. If I got stuck and I cannot do any update, I did not find any substantial update, I am going to output a random hypothesis and halt. So let me give you a pictorial description of this algorithm. At the beginning, everyone is at this point 0, all the WIs at this point 0. And I start with bucket 1. Update happens. If it is substantial, it could kick out the hypothesis to other buckets. Then I move to the next bucket. It's empty, so I move to the next bucket. Here, maybe I don't find any good updater. What happens is that in this case, I'm going to select one of the members of this bucket uniformly at random and just output. That's the algorithm. What is the time complexity, as I mentioned? Here is just, there are a lot of log n's that I'm hiding in this proof, but basically theta of 1 for just checking the hypothesis. And then if it turns out good, I will perform another theta of n. And then you might say, okay, why this is not in a squared? Because this line does not happen very frequently. Every time that I do updates, I'm removing a constant fraction of the elements in the bucket, so this cannot happen more than log n times, right? So the overall time is, if you ignore log n's, is roughly ns epsilon. And s is like the time that I compute the semi-distances, essentially. So it's like n over epsilon many things.
Bunch of hypotheses in it, right? So when you say that HI can cause substantial updates in PL, do you mean that the HI causes substantial update in every hypothesis in PL, or?
No, it means that essentially it can kick out constant fraction of the hypothesis from BL out. That's what we are looking for. That means that the length of the update has to be at least epsilon, so you sort of kick them out, and also it should be many of them. Yes. So why this is actually working, it's related to the minimum distance estimate, and it's a very interesting observation. Like when we get a stock, remember that when I was searching for the updating hypothesis, I searched over every single hypothesis. So that at some point, I have stumbled upon the best hypothesis too. And the best hypothesis was not a good updating hypothesis. It could not update the underlying, like many of the hypotheses in the bucket. And this is the only thing that I'm going to use here. This would imply that those hypotheses that we couldn't move them are actually good hypotheses, meaning that they are satisfying the 3-opt guarantee that I was looking for. For those hypotheses, before that, like I'm going to, again, using the special edge argument that we saw earlier, I'm going to show that the special edge is not exactly smaller than opt, but it's very close to opt. Like it's smaller than opt plus 2 epsilon. And this 2 epsilon doesn't really, it's like effectively you can ignore. So the proof is very similar to the minimum distance estimate that we talked about earlier. So there is one observation about the best hypothesis. So far, now that I got stuck here, I know that any any bucket that comes before this are now empty. Like just by the way that the algorithm works, I start from the smallest bucket, like from the essentially left to right. So now that I'm in this, let's say the elf bucket, everything before this must be empty, which implies that the best hypothesis, the HI star, is also not in here, and it has to be somewhere in here. So I have a lower bound for the current score of the best hypothesis, even though I have no idea which one it is, I have no idea where it is, but I know its score must be high. So when its current score is high, it means that it's higher than the lower bound of this bucket. And I know it's, as I mentioned, it's always smaller than the TV distance. The score is always smaller than the TV distance, means that it's a small, like the lower bound of this bucket is a lower bound, this boundary of this bucket is a lower bound for opt. So I have a lower bound for opt, which is nice. And then on the other hand, I know that the HI star could not update many of the HJs, meaning that the special age that we talked about has to be smaller than the current score of these HJs plus epsilon. Like it couldn't push them out, right? So it couldn't update them by more than epsilon. So that's where the bound comes from. Which implies that, okay, now we know that these are the member of this bucket, so this must be at most L epsilon. So it gives me an upper bound of this special age. And putting these two together, you can show that this special age is bounded by opt plus 2 epsilon. And this is essentially the proof without, like I hide a lot of log factors, and I hope you forgive me for that, but it's like essentially this is what's happening in this proof. Okay, so I think that's it pretty much from my end, and thank you.
Questions?
So if P already existed in your set, so one of the HIs was exactly P, then you want, is that easier or? So opt is 0.
And then you can use pretty much any of these algorithms, and it will give you the right one. Like if it's unique, this algorithm would.
So maybe I'm missing. So if you have, just to test identity testing, you need domain size.
You need a square root of the domain size.
You have nothing with domain size in the.
Yes, so that's sort of the beauty. So, okay, so there are like a couple of, if you go back to that slide, there are a couple of naive things that could work. One is like identity testing to many of them. Another one is like first learn and then find the right thing. But all of them would require sample complexity that would depend on the domain size.
Right. So maybe I'm confusing. I'm asking silly things. How are you getting rid of this dependence on domain completely if there's.
Yeah, because in the whole algorithm, the only thing that I worked with was semi-distances. And you can estimate the semi-distances. Like first of all, there are n squared, and choose too many of them. And it's just estimating a probability of a set. So log n over epsilon squared is enough for my algorithm. There is no, in a way, I am sort of banking, like this whole hypothesis selection works when you have some domain knowledge that this opt is a small. And if this opt is a small, essentially you're betting the best possible things that you can do. Like if you know that the sets that you selected are good, then you can beat this sample complexity. So that knowledge will allow you to sort of beat this lower bound here.
So, sorry, I'll maybe ask. I'll make it talk later.
Okay. Hi. So there are some algorithms for exploring time in like linear time, just without log factors, right? But with a larger approximation factor. So I was wondering, do you think there is a hope for getting your approximation factor in linear time, like pure linear time without any extra log factors?
That's we would love to see that. Like there are linear like n log n algorithms. There is one like O of ns algorithm, but it requires pre-processing time. So we do expect.
Oh, I see. So does our algorithm require pre-processing or no?
No, it's n over epsilon squared time.
Yeah, you can get n over epsilon squared.
So you get a 9 approximation.
But you get larger approximation.
Okay, then. So the data sets that you have.
So I guess it was kind of hidden in one of our papers, which was you can get a 9 approximation, but you just run this tree thing, but you analyze it a little bit carefully.
You don't use all your samples for every comparison. So you can get less than n over s. It's like ns over log.
Sorry, I thought that algorithm. In my head, I was like, that's for discrete distribution, and then you create the data set before, so that's why I didn't mention it. But yes, there is. Sorry about that.
I had a question, which is, I guess from the table, this like MS08 with exponential preprocessing. If I'm wondering why you even need like to spend ns time. Like, couldn't I just store all the answers? Oh, I see. The domain size is infinite or something. Is that okay?
It basically, the pre-processing tells you the essentially it hints you like with what order you should look at the WIs.
Okay, cool.
That's what they do. The pre-processing.
Maybe this connects to the graph session, but it seems like you're kind of like tightening. If you look at graph algorithms for source paths, right? They like have dual variables and they're on the line and they're tightening it over time. Like somehow these W's feels like they're dual variables in some vague sense. I don't know if that's like a connection that's worth thinking about.
I would be like, I actually thought about this problem sometimes. So it's like, I think any connection would be appreciated. Yes, that might be. Other question?
Okay, let's thank Maryam again. And I guess we're gonna restart at 11:15.